Right. So now we're going to talk about energy analysis of closed systems. So we go back to chapter 1 and talk about a system. Um, so we had two distinctions. We were either talking about a closed system. So a closed system means that we were dealing with a control mass, or an open system, which means we were dealing with a control volume. So we're controlling the volume. So in this particular section, we're going to focus our attention on only closed systems. So we're controlling the mass. So that means that for all of our analysis, we're going to be dealing with a system that only has a constant mass. So that means in this particular example, we don't have any mass crossing the boundary at all, and we won't throughout this particular set of conversation. Now, that can be a little tricky because some of the systems we'll analyze eventually for these closed systems might feel like they could be open, but we're going to model them as a closed system, so no mass being exchanged. We definitely will have energy exchange, though. So that could mean we have a Q, or heat crossing the boundary, or work crossing the boundary as we go through. And then the types of boundaries. So we had both the idea of a real or imaginary boundary. For a closed system, these are going to be real boundaries. So we need something to contain our mass, so they need to be real boundaries. And two types of boundaries that we'll see for those real conditions are a moving boundary. So an example of a moving boundary is right here, actually, on the piston. So that piston could move, could move up or down. But it's staying, it's moving. And then the other option in here is that we could have, I'll put it down the edge here, we could have a fixed boundary. Edge, so fixed. So the fixed boundary doesn't move, stays constant throughout the analysis. Okay, so let's go ahead and define boundary work. So if we say that work is our integral of f ds, so that would be from an S1, location 1, to a location 2. We can then write this a little bit differently. So you've probably seen this before, quasi-equilibrium. So quasi just means that we're really close. We're going to assume that our system is in equilibrium. So we'll say, all right, our work, and I'm going to subscript this because I'm going to say work at the boundary. Because we only have one thing, I'll put it in green right here. We only have one boundary that's going to be doing work, hence the topic, boundary work. And we'll go ahead and say that's from 1 to 2, FDS. So what are our different components here? So we can say, all right, well, what's really doing the pushing there? What's doing the pushing is this pressure term down there. So our force term really is thinking about pressure as it acts over the area of that piston that's there. So area of the piston kind of points in this little object is the cross-sectional area of that piston. So really what's the force being applied by all those little pressure arrows? It's the pressure being applied over that area. And then our displacement, which is that ds term there, is how much this piston moves. So we say there it is in ds, but that's not super helpful. So how do we put that in terms of useful quantities in the system? And really the thing that's changing in the system is we're looking at this kind of blue chunk in there, and that chunk is represented by a volume. So we can say, oh, well, I probably could write that a little bit differently. I could say that my volume that's going to be changing is the area. So the area of the bottom of that piston doesn't change, so that's just going to stay area, times the displacement. So really, this chunk in here it looks 2D, but it's actually 3D, is the volume that we're going to be analyzing. So then if I rewrite this and say ds equals dv over area, that's what I'm going to put in for my ds term. So then ultimately what that means is that my work's going to look a little different. So my work at the boundary then, from 1 to 2, so if I put my pressure term in there, that's the first part, my dv term in the second part, there's the A. Let's make that a little nicer. There's the A's cancel. So now my work at the boundary from 1 to 2 is PdV. So my limits of integration change from being position 1 to position 2 to volume 1 to volume 2, right? Because my limit changes. Essentially what I'm integrating with respect to changes. And so if I write this, I'm just writing this out in a different form. I could write this out as a rate. So power, the boundary, so work for time, states 1 to 2. That pressure is not getting a power term, but my volume is. So there's one form, there's another form, and we could also write this as work at the boundary per unit mass. Pressure doesn't get the per unit mass because that's an intensive property already. What we're going to turn into the intensive property is the volume. So little v. Just as a reminder, that little v is volume per mass. Great. So that's our overarching assumption in this particular problem is, parting with this work at the boundary pressure volume component. So let's see it in action. So really when we're thinking about this, we're talking about a process path. So we're working from 1 to 2, or doing work from 1 to 2, or 2 to 3, or 3 to 4. And we're going to see some other examples later in the quarter where we're dealing with this piston moving up and down for an engine, for example. So we have multiple paths to talk about. And so that process path becomes really important. Really, this diagram over here, this PV diagram, is just saying, oh, well, we could have different work depending on the path that we take. So A, B, and C all have different work. And then we'll eventually talk about this idea of going from 2 to 1. So as one direction, and then we could go the other direction, 1 to 2, and one will do positive work, one will do negative work, and so the difference between those will be our network, or what's happening in there. So we're really thinking, as Dolly said, working 9 to 5, working 1 to 2 or 2 to 1, depending on the direction of the piston. So when you write your work, how you write those subscripts makes a difference. So 1 to 2 versus 2 to 1 are the same, really the same area under the curve, but they imply a different direction. Direction is different between these two things. And that's okay. You could also label it, like we did in this path up here, A, B, C, but just recognize that the sign is going to indicate how we move from one state to the next. So let's talk about some specific conditions. So we're going to talk about a constant pressure, a constant volume, and a constant temperature. Then our final case will be something called polytropic. So these are all just special cases of integrating that work at the boundary. So let's get to work. So if I say I've got a PV diagram, so we're going to start using these a lot more extensively. So I'm going to use little v, specific volume. I could use big V, but we're going to start getting in the habit of using big I'm sorry, little v. So in this particular case, what's going to happen is we're going to have constant pressure. So this is a lot like those problems that we saw when we were developing the tables, where we had a weighted piston. We put a burner down here that's represented by heat crossing the boundaries. We increased the temperature of our substance, and our pressure remained constant between those two states. So we can say, all right, well, I really have some specific volume at 1, some specific volume as we increase the temperature of that substance to 2, but what's going to happen is that my pressure is going to remain constant. And oftentimes we'll use a P sub 0 to designate that pressure is constant. So if you see P naught or P sub 0, it just means it's a constant pressure, typically, is what they're trying to imply. And so if you look at this from the perspective of area under the curve, you probably right away recognize that forms a nice box. So you could right away say, oh, well, it's the difference between those V's times P is the area under that curve. If we derive it, so we're going to move from big W to little w. So we do work at the boundary per unit mass. State 1 to 2, pressure d little v. And since my pressure is constant, what happens? Pressure comes out of the integral. And you get exactly what we just said visually there. You end up with pressure and then our specific volume subtracted. And that's it. And like I mentioned, we'll keep it consistent with what's happening in our picture. So P naught, so that's that constant pressure, and that's the work at the boundary. And I could also write this in all of the other forms as well. Work at the boundary in terms of just volume, and I could do it as a rate as well. So 2 versions there that we'll see. So constant pressure. Okay, so let's take a look at constant volume. So this is the example that we've kind of seen before. So we're still possibly seeing heat cross the boundary. So it doesn't mean that there's nothing happening on one of the boundaries. It just means that our container is not changing volume. And picture that you saw up there is Asia. So heat of the moment is the only thing that crosses the boundary since the volume is constant. Or in other words, we do not have any boundary work. As you probably imagine, right? There's no work actually happening at the boundary because what's happening to our pressure, we're going from, let's say, P1 to P2, and we're going vertically here because we don't change volume. Might change pressure because we're adding or removing heat, moving heat across the boundary there. But since there's no area under the curve, we would say that our work at the boundary is equal to 0. Probably say, well, that seems kind of obvious. It's true. But I think the thing that usually tricks people is the heat component. You sort of assume that there's some kind of work being done at the boundary. There is not. Constant volume, no work at the boundary. That does not imply no work. It just means no boundary work. So no boundary work. Just be careful. But you're thinking about that piston scenario. That's what we're imagining. So isothermal, so iso meaning same. So thinking same temperature. So an isothermal scenario here. And This is specific for an idealized gas. So we need to check. We need to check that we're actually dealing with gas here. If not, then this is pretty much junk. But I already kind of pre-built the diagram, so this is what we would expect from an isothermal looking scenario. So constant temperature, so our T1 to T2 is the same. So T1 to T2 is the same. So really what that implies is if we're thinking about this from a um, ideal gas equation, so we could write little v, sure, RT. Then if our temperature remains the same, we're essentially saying PV over R for temperature. So we can say PV 1 R equals PV 2 over R. It's the same R, so that goes away. So our relationship really, I just put the 1 outside the parentheses there a lot of times to make it a little easier to see, is this. Or you could say if the mass doesn't change, so it's also valid to say that this relationship holds up. So pressure volume combo is equal to each other. So the pressures aren't equal and the volumes are not necessarily equal, but we know that the temperatures are equal and our masses are equal. So just as a reminder, M1 is equal to M2, T1 is equal to T2. I know I wrote that already, but it's just good to remind yourself of that. So when we actually do calculate our boundary work here, so work at the boundary, I'm going to go with capital B this time, just to be a little different. So we'll say 1 to 2 pressure dV. And so what we're going to say is that based on what we just wrote up here, we're saying that that combo of stuff is just equal. Let's call it some constant. So that constant, the P times V, is always going to be constant. Yes, independently, pressure and volume are going to be different, but the combination of them multiplying together will always be equal to each other. So that means that we can say, all right, well, in that case, we could write this as pressure is equal to C divided by volume. So it could be volume from 1 or it could be volume from 2. Choose your favorite subscript here. I'm just generically saying P and V here for a second. So if we put that in here and we do the integration, something happens. So we know that in this particular problem, C is the thing that remains constant. So yes, it's a combination of pressure volume, but it remains constant. So that comes outside the interval. And then I'm left with this 1 over V dV component. And so what comes out of that, if you remember calculus, you'll end up with a natural log. So we'll see C natural log of our volume as it's evaluated from state 1 to 2. And it's really from volume 1 to volume 2. So we could just write this a little bit nicer and say natural log of V2 minus V1, or if you remember how to combine natural logs, you'll say they're divided, right? Remember that natural log V2 minus V1 becomes this. And so this work at the boundary, it becomes a little bit more complicated, but it's more of a choose your own adventure work at the boundary. We can say, all right, our work at the boundary really is C natural log of V2 over V1. And because we have this relationship of PV equals PV, if I move my P's to one side, my V's to one side, I can rewrite this relationship here to also be natural log of the ratio of my pressures. Just remember that the pressures are the opposite orientation as the volumes. So that's totally valid. And the C, you can choose your own adventure here. So your C can either be the combination of pressure volume from state 1 or the pressure volume from state 2. You need both in order to find that C. And that is your work at the boundary. Ooh, that's a terrible color. Work at the boundary for this particular case when we have an isothermal scenario. So there we go, those two. It's also kind of nice just to remember these combinations of things, but that's what you'll use. You won't need to derive the equation, which is not too terrible, but it's nice to know where it comes from, so it's not totally out of the blue that you're using these things. So really what we just solved um, was we just solved a specific case of something that's called the polytropic property. So we're thinking about poly or many. Um, then um, what we're really talking about is that instead of PV equals a constant, we're adding an exponent to how that volume relates to the pressure. So in other words, when n equals 1, that's a special polytropic case where we have a constant temperature, or isothermal. When n is greater than 1, that's what we typically call the polytropic case. That's nice because it really tells us that we have really one scenario works between the two cases. Now, there's a little bit of problem. We'll derive the equation. The equation that we're going to derive assumes that the n is greater than 1. Um, so if you do know you have an isothermal case or an n of 1, just go right to that equation that we just had. Okay, so polytropic is kind of weird. It looks similar to the isothermal case, but when we don't have constant temperature, so temperature varies a little bit on either side, really what it means is that our volume is going to change in this nonlinear fashion, actually exponentially different, with the combination of it being multiplied by pressure. We're not going to dive too much into the science here, other than saying that this is going to produce some, I would say, some more interesting boundary work. So when we talk about our boundary work, going back to our equation that we came up with earlier, so pressure, volume. I'm not going to derive those directly in here, but the idea is if we do a similar sort of thing that we did before with that C, so in other words, we rearrange this P and we say that's C divided by our volume to the N. And then we say, oh, okay, well, really the other things to think about that C is that it's P1 V1 to the N, P2 V2 to the N. Something that does remain constant for these cases is the N will be constant between the two states. So N is something in this particular case that relates to the substance itself. So you'll either be given the N or you'll have to find the N, but it will remain constant between the two different states. We're not changing substances, therefore our N is going to remain the same. So you can do the work and calculus here. I'm pretty sure most of you would fast forward this anyways if I spent time deriving it. But you'll end up with something that looks like this. And then downstairs, you end up with that 1 minus n, or negative n to the plus 1. I wrote it like that because this is how I think about doing the integration, the plus 1 or adding 1. And then we're going to evaluate that between states 1 and 2, so v1 to v2. And ultimately, what that gives us is work at the boundary. If you plug in that v2 and v1, you can say, all right, well, end up with something that we can boil down to this. And that's the form that we'll make use of. So something that I didn't mention yet is, notice that one of our caveats that's not on the slide, and that's the idea of ideal gas. So this equation is assuming that you have some gas. It does not need to be idealized. Actually, that's kind of the point here of it being polytropic, is that we don't necessarily have a well-behaved gas. We could, but we don't necessarily have a well-behaved gas. If we do have an ideal gas, what do we know? We know that we have that compressibility factor, Z, and that Z is going to be equal to 1. Therefore, ideal gas behavior, which means that our work at the boundary can then be approximated with this, which kind of makes sense if you go back and plug stuff in, but I'm writing it out for you so you don't have to do the algebra. 1 minus n. So it looks pretty similar, right? It's just basically saying that those two pressure things get rolled into an MR component. And then we end up with this lovely form. Just make sure that you've checked to see if your substance is ideal gas, which you need to do anyways. Okay. So if you have something that has boundary work, and also at that boundary, so not only do you have this boundary here and potentially some work that's happening, but then you also have a spring in that particular system. So there's no special name for this other than expansion against a spring, or could be contraction against a spring too, especially if the heat were going the opposite direction. We can essentially say, okay, well then in this particular scenario, my work total is work that I have as my system expands. So that's work on the piston. So that's this chunk right here with constant pressure, right? That's that very first work at the boundary scenario we talked about. So it's either expanding or contracting, plus my work from the piston. I'm sorry, from the spring. And so work on the spring is linear, but it forms this little triangular chunk of work. So essentially it increases pressure linearly as we push more and more on the spring, which kind of makes sense, right? Because that's essentially that's our slope of how much our pressure is increasing, um, as we compress the spring more and more. Or if it's going the opposite direction, uncompress the spring. Thing to note in here that just kind of gets people in trouble is that negative sign means that work is coming out, plus is work in. Um, yeah, so I kind of generically wrote the plus in there, but just be a little careful with your signs. Okay, so again, this is just a review component for first law. So I do expect that you start with things here. So again, just a refresher. So work for the general case is Qn, work in, Q out, work out, and that's equal to your change in internal energy of the system, kinetic energy of the system, and potential energy. So for now, so these all get little system subscripts. I'm just going to underscore them, highlight them. For now, we're not dealing with closed or open systems, so keep that in mind. And our work can be any different form. It could be work mechanical, electrical, um, nuclear. There's all kinds of works that we could have in our system. Stationary. So remember the stationary scenario just said that our kinetic energy of the system was equal to the potential energy of the system, which was just zero. So it means that our system itself has no motion, no velocities, no changes in velocity, I should say, no changes in elevation. An airplane in steady level flight, constant velocity, constant elevation is a stationary system. Kind of breaks your mind a little bit because you think it's moving, not stationary. But um, if it's not changing elevation and it's not changing its velocity, then we're considering stationary. So think statics, right? So no accelerations. And in that scenario, if we say, all right, well, our Qn minus our Q out is really our Q. So if we define for the stationary system work to be work out minus work in, this is a little weird because this is different what we just wrote at the top. So for this general equation. But it's pretty common that you'll see this. So the reason that sometimes folks write it this way is because it's more thought of net Q coming in means it's positive. So in other words, um, more Q in coming in will give us a positive term for Q. So we're thinking about heat coming in. When we think about what we have systems for, typically the idea is that work coming out is the thing that we want. So we can say that net work out being positive results in a higher work out term. I don't love this designation, but this is a designation you see quite often. So in other words, the form will look something like this. These two things are not equal to each other in those forms. I mean, they are. It's just that the signs have shifted on the work. So whenever you're solving problems, if you use the Q minus W equals delta U designator, you have to be very clear that you're specifying that work out is positive versus work coming in being positive. I don't typically love that, especially for new students. I prefer this first form. And for a stationary system, it looks pretty similar for us. We could say for us, that stationary system would be Q in, work in, both positive, Q out, work out equals delta U. This is the form I prefer generally because I think it's less confusing, but it's not uncommon, and you'll see this in a lot of text, including textbook that we typically use for this class, being in that form, the Q minus W. Just remember you're making a sign change if you use the Q minus W. But not a lot of people pay too close attention to that. Similar sort of thing, if we do this per mass, it's not much different. you could do Q minus W. This is the form you'll see pretty frequently. But the form I prefer is that full form. I don't mind that people switch to that. I just think that early learners of thermo tend to get this confused if we switch signs. So I prefer the ones I boxed there. And in class, as a practical perspective, when you're problem solving, if you state that something is stationary, you can jump right to these two equations here. Either one of those is perfectly fine in form. If you do use Q minus W and you don't state that work out is positive or distinguish that, then I will make note of that in your assessments. Okay, so let's talk about a special case. So that special case of constant pressure. So I put the goofball formula in there, the Q minus W. So let's look at it from the perspective of writing this out. So I'm going to use the Q minus W form just because that's commonly what you'll see. So if you write this as Q, and then we say, all right, well, in this system, really the only work that we're going to have, and this is going to be starting to be the common thing when we talk about work in general, just a note for these systems. Your note is that in general, your work is going to be some combination of work at the boundary and what we call work other. So that work other could be things like mechanical work, so it could be a shaft, propeller, it could be work electrical. Those are the most common that we'll see in this class. Generally, it's some combination of those things. So we're breaking up work into work at the boundary, so a moving boundary plus other stuff. Now I'm going to tack in here work at the boundary plus work other. And that's going to be my change in U, or internal energy. Put this term to the other side. So Q equal to, or minus, I should say, work other, delta U plus our work at the boundary. And now we can say, all right, let's look at the right side of this equation. So let's focus in only on that delta U and work at the boundary. So what's work at the boundary for constant pressure? We would say, all right, well, that is P naught B2 minus V1. It's my difference in volume. Or in other words, I can say delta U. If I put this in terms, instead of P naught, I call it P2 V2 minus V1 V1, right? So we're saying that P naught is equal to P1 is equal to P2. My pressure is constant. And if I expand that a little more and say U2 minus U1, so my internal energies, P2, V2, P1, V1, we get an interesting form. So this interesting form in here is we can combine some like terms. So we can say, all right, our twos are stuff that happens at state 2, and our stuff that happens at state 1. So what we're going to designate as the stuff in there is a term called enthalpy. So enthalpy will be what's happening to my internal energy plus that pressure of volume at a boundary kind of rolled into this one term. H1, U1, so P1, V1. Or another way that we'll be writing all of that is we'll just say H2 minus H1 for this special case, the constant pressure. And we can also write this in the form of little h's, which we can find in the table.